board. And this was exciting in many ways. We've been talking about the basics of what we call set theory. And why this is important is there's many reasons this is important. Perhaps the easiest way to explain it is that sets occur in nearly every branch. In fact, they occur in every branch of mathematics. So they're the first thing that we technically are working with in this class. It's a mathematical object. So basically what we did last class is we talked about the definition of a set. We talked about subsets, talked about the empty set. And one of the things that we do in mathematics, and this is really only familiar to you guys in a few ways, is once we have objects, we like to know what can we do with them. Can we build new objects from old objects? And if we can, how do we do it? So we showed you last class, you know, if I have a set, then I can look at all its subsets and I get this new object called the power set. And that turns out to have lots of uses. And then you might ask yourself other questions. Well, how do I get other sets out of other sets? And of course, you might say, well, I don't care about sets. And I say, that's fine, but you're in a math class, and the math nerds do care about creating new sets from old sets. We care about analyzing sets. And it turns out it's useful, just as you learn as a kid that adding, subtracting, multiplying, dividing are useful. And then as you get older, you learn that replacing real numbers with letters that can represent an arbitrary number is useful. Turns out algebra is useful. And then we realized that studying the relationship between two quantities, maybe we call one x and the other y, is useful. And then we have these ideas called functions. And then we realize that these objects can be played with. We can add them, we can subtract them, we can multiply. And then we can do all that kind of stuff, like compose them. We can integrate them. We can take their derivatives. There's all kinds of cool stuff we can do. And now we're kind of regressing. Now we're going in a very abstract manner. We're saying now a set is any collection of objects. And what we want to know is, what can we do with these collections of objects? How do we sort of play with them, like my kids play with Play-Doh? What can we do? And you've actually done some of this without specifically being told that's what you were doing in a math class before. So anyhow, does anybody have a question or comment before we begin on this? I had a dream that I woke up today, this was on Friday, and that the Roni was gone and we no longer had to wear masks. I was so excited. Yes. Did you have the same dream? I wish. Okay. Anyhow, and so let's pick up where we left off. I think the last thing we talked about was the cardinality of a set, basically how many objects are in it. We want to be able to count if we can. Is there 5 objects in it? Is there 100? Is it infinite, but is it infinite in a way that we can keep track of its infinite? Like, for example, the numbers 1, 2, 3, forever and ever and ever, that's an infinite set, but there's a pattern that we can sort of order it in, right? Whereas if I said, can you list the numbers between 0 and 100? All of them. You couldn't do it. Now, you don't realize that yet in a rigorous way, but you can't. I mean, you imagine, how could you, I mean, you could count off numbers. You can count off the evens. You can count off the odds. Hell, if you wanted, you can count off the rationals. You could say like 1, -1, 1/2, -1/2, 1/3, -1/3. And you could sort of see some pattern or recite all those things, but the numbers in general, you can't do that. So one of the things we'll get into maybe in this class, but maybe not, is this idea of that there's different sizes of infinity. It's a pretty cool thing to ponder if you're interested in that kind of stuff. Okay, and then we also talked about the first way we constructed, if we had 2 sets, how do we get a new one after the power set, is we say, okay, we can do this Cartesian product, which you guys have seen before, even though we never called it that. When you look at the XY plane, that is taking the real numbers and the real numbers and looking at pairs of them. All right, So let's pick up where we left off, and the place to leave off is some new terminology. And you've seen these symbols perhaps in a math class before, but they were never officially defined. We would just give you an English translation of them. So what are they? I shouldn't say we now can. That sounds silly. All right, so let's take two sets. And for the lack of more creativity, I'll call one A and B, the other B. Now I'm saying nothing about them. Maybe A has numbers in it. Maybe B is the name of car manufacturers. Maybe both of them are names of, one's the name of presidents, the other's the name of rivers. I don't know. They could just be a collection of something. I don't care what they are. So what we do is we define their union. So the set A, we're going to put a U like this. It looks like a U. This is called the union of A and B. Now, this is going to sound silly, but you got to be very careful with the English. So what this means is it is the set of all points, or I shouldn't say points, that's a bad word. It's a set of all elements that's in, or that are in A or B or both. So we're going to do an example in 30 seconds, and it'll make this clear. But there's some analogy here with what we call the disjunction when we were doing propositional logic. The disjunction meant P and or Q. And that's similar to what we're saying here. This union means, and maybe I should write this a little cleaner here. It means that you can be in one of the other or both. And then there's a very closely related thing called the intersection. So the set A, and then we write an upside down sort of U. So this guy is called the intersection of A and B. So this is this set all elements in both
What'd you get instead?
A and B. So there's a subtlety here. These loquacious people on the other end. Yes.
So if in the first one, union, we're creating another set, right?
That's okay. So so the question was, are we creating another set? Sort of. I guess you could say that because you're creating a set that has a certain property. Yeah, you could say that you're creating a new set.
So if A and B each had a member that was the same, say if we were doing the integers in different sets that contain integers, and both of them have 5 in there.
Yeah.
Would that union then have 1 5 or 2 5s?
Well, let's look at it. No. So let's do an example. The best way to see it is, so the question basically was asking, if your 2 sets had a 5, what would the union look like? Well, let's see. So let's take, for the sake of argument, let's take the numbers 1, 3, 5, and 7 for A. So it's the first 4 odd integers. And let's let B be the set 2, 3, 4, and 5. Right? So these are two very sort of elementary looking sets. The first set is some odd numbers. The second one of the integers 2 through 5. Okay, so what is the union? The union is everybody who is in A, everybody who is in B, or in both. So what would the union be? The union would be 1, because it's in A. What about 2? Well, 2's in B, so it's there. 3's in both, so we're going to count it. 4 is in B, so it's in the union. 5 is in both, so it's in the union. And then 7. Now, what is the intersection? Well, the intersection is the set of only the people who are in both. And who is in both? The only guys that are in both are 3 and 5. So you're not going to count it twice because, remember, if our definition of a set is a collection of unordered objects, right? And so we're not going to count it twice if it's in there. Fair? Okay. Ponder that. Why count it twice? Why count it 3 times?
I can see it either way. That's why I asked.
It's a good question, but it's one worth pondering. Does anybody have a question about this example? Going once, going twice. Someone has a question. Yeah, you might have, Josh. Yeah. You probably did. You probably learned about Venn diagrams, and I think that's part of high school curriculum now, basic set theory and stuff like that. So hopefully some of you, look, it's always a good thing when we're going to teach you some stuff that you've seen before. That's very helpful. That means that when you learn new stuff, you have less to learn. So there was a good question though, like for example, since 5 is in both A and B, in the union, should we count it twice? And we're not going to do that, but I would encourage you to think about why you would want to and why you would not want to. Think of, if you're curious about it, ask yourself that. What would be the pros and cons of both sort of conventions?
From one perspective, they both represent the same quantity, but then I can also see that they are just individual objects. It could be the amount of, we don't know what these things represent. It could be 5 of something. Maybe we want to add this setup together.
Right, but so again, let me phrase it this way. I'm telling you the convention is, we're going to count it once, but it's not a bad question for you to ask why, and it's not a bad question for you when you have some time to think about why we would do it the way we're going to do it, and what are the pros and cons of the other way. And a good piece of advice I can have for you on that is to think about what happens going forward. So we can write these things symbolically. And this is going to be scary, but I did tell you this on Wednesday that you should try to get comfortable with all this sort of fun stuff. So in symbols, A union B, what is it? It's the set of all elements, I guess I'll use X, such that X is in A or X is in B. And then A intersect B is defined as the set of all elements X such that X is in A and X is in B. And then it's always nice to also look at these things in terms of pictures. So we're going to do that. And the picture we talk about is what's called a Venn diagram. So we're going to draw two of these creatures. So one way to talk about how these things interplay on each other is as follows. So what we typically do, for those of you who are unfamiliar with a Venn diagram, is we think about, we have two sets. We'll call this one A. We'll call this guy B, and then this is A, and this is B. And then we like to think about these sets sit in some universe somewhere, just like we live in some universe, right? Right now we're on Earth, right? But we're in this solar system in some universe, if you believe in all that kind of stuff, right? And so we imagine that there's some universe somewhere that has all the sets that there can possibly be. So right now, A and B are sitting in that universe, which we'll denote creatively as U. So what does the intersection look like and what does the union look like? Well, the union would be everything that's in A, everything that's in B, or everything that's in both. So right here, this is A union B. Now over here, we just want what's in both. So we're drawing two circles with this little piece highlighted in red to illustrate that this is what's in both. Does anybody have a comment or a question about this? So what we're really doing, a better way of saying this, and you're not wrong what you said about creating new sets, that's what we're doing. But a more general way of saying that is we're defining operations on sets, just like we can operate on numbers, right? Or we can operate on functions. What we're doing is we're creating, or I shouldn't say creating, we're defining operations. Okay, does anybody have a question about this? Now, one of the misleading things is it's possible that A and B don't overlap. Right? So the pictures that I've drawn here are in the scenario that they overlap. It's possible that they don't. I mean, take the odd numbers and the even numbers. Do they overlap at all? Not at all. So what does it mean if they don't overlap? So suppose A and B are such that when I intersect A and B, I get the empty set. They don't overlap. So in this case, we say A and B are disjoint. Does anybody what? I'm stuttering with my mask on. Does anybody have a question or a comment? So again, right now, this might be boring to some of you, and I can get that, right? We're kind of like, one of the things that mathematics does is it tries to nitpick and generalize as much as possible. And that's what we're doing right now. We're setting the foundation with the most general sort of objects that we can deal with in mathematics, and that is a collection of things, which we call a set. Another important operation is called the difference. So we're sort of just going with our intuition here. The set A minus B is called the difference of A and B. That's bad. Poor language, O'Grady. So this is, think about what we want this to be. I mean, you would imagine if we say A minus B, we would then think, well, this can be all the objects that are in A, but not in B. So we're going to take B away. Oh, I can't write. So this is the set, or this is all the elements in A, but not in B. So let's just write down what this means in symbols, because you got to get comfortable with this notation. This is the set of all elements X, such that X is in A and X is not in B. Now, there's also a synonym for this, which some books, if you go on the internet or textbooks, might use. So A minus B is also called the complement. We can't spell today. It's complement, E. So you gotta be careful. It's called the complement of B with respect to A. So some alternative sort of notations. And let me go back in case some of you need to copy this down. Every book sort of uses different notations. I shouldn't say every book does. I mean, look, there's different fields that use this stuff. So some of you may be familiar with some probability. In probability, all this terminology is sort of the same, but we use things like complement. You know, If it's a 30% chance it's going to rain, the complement is it's a 70% chance it doesn't rain, stuff like that. So sort of these, historically, a lot of these things were developed in different disciplines, and so sometimes we use just a little different language or different words. So, you know, you can't, basically what I'm trying to do is I'm trying to sort of give you the fact that if you go on the internet looking for something, you might see different notation. Does that make sense? Maybe. So another sort of way you might do this with some different notation is so we might write something like that A minus B. So let's think about what all this is. So this is sort of, it's everything that's in A but not in B. So we might also write it as A, and this gets confusing for some people, this backslash B. So some people like to read this as like A take away B, maybe. And some other notation that people might have is, instead of writing it as A take away B, or as A minus B, is another sort of universal notation is to write B with a power C. So let's look at a Venn diagram of this real quick. I think it helps sort of make sense of this. So if this is our unit, let's take some circles here. So let's take, if we call, get my marker. If I refer, again, this is my universal, this is everybody. And then let's say that this is A, and let's say that this circle represents B. Again, don't get overwhelmed here. These sets can have anything. They can be numbers, they can be anything. Names of, you know, names of men or names of women or computer brands or, I don't know, light fixture brands. They can be anything. They don't, you know, so we're just representing it with a circle. Well, what would A take away B be? Well, A take away B would look like this. It's everything that's in A but not in B. So it would be me shading in A, but I'm ignoring this little piece that's also in B. Now, there's some context issues here. The complement is defined, you know, notice that if we look at here, if we just say the complement of B, there can be confusion. That's why we add this sort of thing at the end. We say the complement of B with respect to A. So when you're talking about the complement, you have to be very careful. What is the larger set that we're thinking about it sitting in? Are we thinking about it sitting in A? Or are we thinking about it sitting in some other set? Or are we thinking about it in the whole universe? So there's very much, you have to be very careful. And I guess we should be, if we're being completely fair, sometimes we also denote the complement like this. Some people denote it as B with a bar over the top. Although this is different, you know, the problem with some of these notations is in different branches of math, they mean different things. So when I was a kid in 3rd grade, Mrs. Karp was my teacher. No, this is 4th grade. I lied. In 4th grade, Mrs. Karp, and we always used to have to do these things where we had context is key, context clues, context, and that is extremely important in all aspects of life. But in mathematics, it means everything, because if I write a minus b here, like on this board, this is not normal subtraction, right? So context is important, and at this level, you have to be able to understand context. And so let's make it very, very clear with this next statement. So caution. Do not confuse if I could just learn how to spell once in my life. Do not confuse the complement of B with respect to A. So that's one thing, with the complement of A. So what is the complement of A? If we just say the complement, if we're not specific with a respect to, then by default it means the whole set, or excuse me, the universe. So let's define that. So the complement of A is also denoted, this is going to be scary, it's also denoted A bar, or say maybe A superscript C. And what this means is it means U minus A, where U is what we call the universal set. So the best way to see this without getting all worked up is to just draw a Venn diagram. So if this is my big set U, then what is the complement of A? Well, let's assume A is some circle. The complement of A is everybody outside of A, but still in the universe. So this kind of stuff takes a while before it starts to sink in, especially if you haven't seen it before. It might, as I said previously, it might seem boring, like we're just doing a bunch of, defining terms, but it's not just that. And when we give you problems with concrete sets A and B, you got to learn to work with them. You got to learn to be able to do this kind of stuff, determine complements. Does anybody have a comment or a question? Now here's the thing, and you have to be prepared for this. Just like if I give you 2 numbers and you can add them together, 4 and 3 is 7. Okay, cool. Well, what if I give you 3 numbers? Then you got to add those together, right? All right, or 5 numbers. So the point I'm trying to make is there's no reason to say that we can't keep taking unions and intersections. And in fact, that's very important in a lot of different ways. And so now that we're like, you know, sort of big kids now, as we like to say, or maybe that's a bad way of saying it, big kids. It's not fair either. We have to be able to do that kind of stuff. As they say now, your mathematical maturity should be of the height where you can now do such advanced things. Okay, so let's do sort of an important thing. And your book lists all these, and we're not going to list them because you can read it if you want. But there's lots of very important set identities that are worth knowing. And we'll probably ask you to prove some of them for homework. And, you know, you might have some struggling with this, but hey, that's what we're here to do. We're here to learn. So let's do that. Let's prove some what we call set identities. So I'll do like 2 of them, and then we'll give you some to practice for homework. So the first one we'll do is one of my favorites. That is, we're going to prove that A take away B is A intersect B complement. So let's assume that, well, we'll write this down in the proof, but in the context, we're assuming that we have 2 sets A and B, and they live in some universal world. We'll call it U. So first off, we talked about this last week. How do you show 2 sets are the same? So to do this, one way of doing this is we must show each set is a subset of the other. So that means if we're going to use this proof strategy, which is a legal one, I have to show that the set A take away B, or the difference of A and B, is the same as A intersect B complement. So there's a couple ways we can do this. This is the one way we're going to do it, and then we'll do it in another way as well, just to show you how that works. Question? It's one thing that we should understand that, you know, you might want to get a feel for what this looks like using a Venn diagram. You might want to say this guy's Venn diagram is the same as the other guy's. That's cool. That ain't a proof. That's a good illustration to help convince you and help get your mind started, but it's not a proof. So we are going to do it this way. And by the way, what I would also encourage you to do, to think about, is while we're doing all these proofs, think about all the P's and Q's nonsense that we've talked about before. That is all underlying this. So let's assume what we'll do is we'll first show that A take away B is a subset of A intersect B complement. So how do we do this? Well, let's take a element of A take away B. So let X be an element of A take away B. What does that mean about X? What can we say about it?
Definitely an A.
Well, we know that. Then X is an element of A, but X is not an element of B. Right? Since X is not in B, X must be in the complement of B. That's the definition of the complement. And then, thus, X is in the intersection of A and B complement. And we've proven that A take away B is clearly a subset of A intersect B complement. Oh, by the way, I'm using two different notations. That was not cool of me. Let's be consistent. So go up here where this C was. Let's just put the old-fashioned vertical bar here for complement. We won't use the C here. So what we've done is we've shown that A take away B is in fact a subset of A intersect B complement. How did we do that? We took an element in there. So we took an element in A take away B, and we showed that element is also in the intersection of A and B complement. All right, now we have to go the other way. Before we do that, does anybody have a question? Comment? Concern? All right, so now let's take X in A intersect B complement. What does it mean to be in there? That means that X is not just in A, but it's also in B complement. Well, and thus X is also in A, and X is not in B. So by definition, X is an element of A take away B. And so this proves that A intersect B complement is a subset of A minus B. And we conclude that A minus B is in fact the same set as A intersect complement B. Question?
If they're subsets of each other, they have to be.
That's right. I mean, that's the only logical explanation. So the comment was, if one set's a subset of the other and vice versa, then they have to be the same set. If I tell you that X is a number that's always less than or equal to 2, but X is always greater than or equal to 2, then what's the only logical conclusion? X has to be 2, be the same thing. Now, there's an alternative way we could have written this that uses a little bit different language, and we'll show you that as well. Does anybody have a comment or question about this? So we typically end a proof with, like I said, this sort of little box. This tells the reader that the logic is done, the proof is complete. We can celebrate.
Why is the box about a triangle?
I don't know, it's just convention. I mean, typically it used to be you write QED, which is Latin for think it's that which was left to be explained or something. What's that?
From Euclid.
I think it dates back to, I don't know if it dates back to Euclid, because they wouldn't have spoke Latin in ancient Greek.
Explanation.
Yeah, something, yeah, right, because Euclid had his sort of, Euclid is sort of, maybe not just him, but that Greek culture is attributed with having this axiomatic approach to mathematics. Okay, let's look at an alternate proof. It's nice to see that there's more than one way of doing it. So alternatively, we could have argued as follows. So we might have said, okay, A minus B, what is this? Well, what's the set of all x such that x is in A and x is not in B? Okay, so what's another way of writing that? Another way of writing that is that x is in A and x is in B complement. Well, what does it mean to be in A and in B complement? That means x is in the intersection of A and B complement. And so, of course, that is just A intersect B complement. So that is also a logically sound argument. So you might ask, why present two proofs? Or you might say, which one should I use? Well, it doesn't matter. It turns out that in some situations, arguing using what we call set builder notation like this is the way to go. Other times it's not. Other times you might want to argue the way we did the first time around. So I'm going to give you, like I said, I'll give you some of these to practice, and what you should sort of think about is like sort of the analogies to like numbers. For example, if I take the number 5 and I add 0 to it, I get what I started with, 5, correct? And so there's, and we call that the identity, right? And so sets have identity operations too. For example, if I take any set A and I take its intersection with the universe, with everything, it's just A. Or if I take a set A and I take its union with, say, the empty set, well, it's still A. And then we know things like 5 plus 4 is 4 plus 5. So we would expect that there's some commutativity with sets as well. I mean, A union B should be the same thing as B union A, you would think. And then the intersections as well. And then we had things with numbers like associativity. There's an analogy here. We had distributive laws. There's an analogy here. What else? With our propositions, we had the De Morgan's laws. There are analogies here. I mean, you think about it. We had, with conjunctions and disjunctions, we had these things called the De Morgan's laws. We proved one of them on the homework, and we did the other one in class. There's an analogy here. For those of you who have ever had probability, you know that there's this thing we call the law of total probability, where if If there's a 30% chance it's going to rain, that means there's a 70% chance it won't rain. And what do those numbers add up to? 1, right? Or 100%. And so the same thing happens here. If we take a set A and we take its union with its complement, then we should get the whole universe. The probability that it either rains or doesn't rain is 1, 100, right? Then if I take a set A and I intersect it with its complement, I should get the empty set, nothing, right? It can't both rain and not rain at the same time. You can argue it can rain and then stop, but we're saying it at the same instant. So anyhow, the reason I mention these things with probability is because there's a very big the language is very much crossed over and really in most all of the advanced mathematics that you guys will encounter. And when I say advanced math, I'm basically talking about things after calculus. That sets play a huge role. They're the underlying thing. I mean, we even talk about it without saying it in calculus. The set of all continuous functions, or the set of all differentiable functions, or the set of all integrable functions. So you learn things in calculus, for example. You learn that if you're differentiable, then you're continuous. And so that means that every differentiable function is continuous, but not vice versa. So what does that mean in terms of sets? Well, that means there's functions that are continuous, but not differentiable. So the continuous functions are a subset of the differentiable functions. Or is it the other way around? Say that again. Right, so let's take a point. If you're differentiable, let x be, well, let's use f. Let f be differentiable. Is f continuous? Yes. So you can easily prove that the differentiable functions are a subset of the continuous functions. But it's not the other way around, because I can find a continuous function that's not differentiable. For example, the absolute value function is not differentiable at the origin. It has that sharp point. So think about that. So we don't really use these ideas in elementary calculus, but in advanced mathematics, when we're studying what we call analysis, which is the theory of calculus, we use sets all the time. Some of you will take classes in in linear algebra. Maybe some of you know things about matrices. We'll cover some matrices in here a little bit. Certain matrices have certain properties. So we say this is the set of invertible matrices, or this is the set of symmetric matrices. Sets are everywhere. And now you're going to get to start to see that. Does anybody have a comment or a question? Everybody bored? Having fun? I hope you're not bored. Let's make that comment that I alluded to before I did all this, and I apologize. So note, we can take the union and intersection of any finite number of sets. Now this is going to look very, very scary to you amateurs, but here's what it looks like. So let's take the union. Suppose we have n. So the union a sub 1, a sub 2, a sub 3. All the way up to some number n. We have this shorthand notation that this is the union. K goes from 1 to n of a sub k. So this notation should be similar to many of you from analogous, at least, to when we did summation notation in calculus. And then, of course, we can do the intersection as well. So don't get afraid of these subscripts. As you know, that this is sort of what we do. We can't, there's not many other logical ways to represent that we might have 100 or 1,000 or 2 million sets that we're trying to intersect. And of course, you might say, who would want to do such a thing? What's that?
I would.
Yeah, it turns out it's useful. In fact, even more wild, it turns out that you can do not just finite numbers, but I can intersect infinitely many sets if I want. You don't want to jump too far ahead right now, though. But you can. So later on, we will, you might say, for example, you want to get to a question I believe you asked last week about the numbers. How could I generate the natural numbers? Well, I can start with the set 1, call that a sub 1. And I can say a sub 2 is the set 1, 2. And then I can keep unioning that in that pattern forever, and I've generated the natural numbers. Does that make sense? It's scary, though. But we do have to say that, even though we don't like to see it. So we can even do this for, now, we haven't really gotten to the words uncountable or countable in this class, which is are important concepts. But those of you who have had calculus 2 understand that there's a way to sort of add up, if you will, infinitely many numbers. We call it an infinite series. And it's really not any magical thing. It's a very intuitive thing where you talk about a limit hiding out in the back of this. And I don't want to get into all that right now because it's sort of off topic, but the idea is that you can definitely do this for, and I use this word lightly, but I can say infinitely many sets. So what do I mean by that? Well, I mean, we could take a sub 1 union a sub 2, and then that union goes up to, say, some number n, but then we keep going. And how would we denote this? Well, instead of saying k goes from 1 to n, we say k goes from 1 to infinity. And then a very similar notation for intersections. Remember, these ellipses tell us that the pattern continues. Oh, this should be an equal sign. So a good application of why we care about stuff like this is sort of what I pointed out to in calculus, or about the calculus example earlier. Or let's even go further back in your math. Let's go back to something as simple as basic geometry. You guys know that every square is a rectangle, but not every rectangle is a square. And you could talk about subsets of shapes. And then, that's cool. Little kids get that. But then you can get even more interesting. You could talk about rotations of shapes. Like, imagine you have a triangle or a square or a rectangle in the plane, and you might ask, what happens if you move that shape, or how can you spin it, or what happens if you take it from here to there, or you shrink it, contract it. Then you could study these things. In the branch of math that does that is called abstract algebra, where you study how, it's technically group theory is the fancy word for it. But you study things like transformations on shapes. Do they preserve things? Do they preserve, what can I do to a shape where it preserves its geometric integrity, its size, its area? So the notion that it might seem silly to talk about abstract sets, it only seems silly to you right now because there's really no apparent reason for you why anybody would care. And so what I'm trying to do is give you a little information on why we might. I mean, if we go back to our calculus example, which we'll go back to over and over again, because that's usually the math that's most recent in your minds here. It's nice to know that if a function's continuous, then it's integrable. It's nice to know that for theoretical purpose, for practical purposes. So it's nice to know what sets of functions are subsets of others, because then we get information for free. We don't have to work for things. It's nice to classify other things. Some of you will take classes called differential equations, where you study sort of these equations that arise in places like physics and biology that describe the world around us. And it's nice to know when these equations have solutions and when they don't. And we classify these types of solutions based on certain things. And when we use the word classify, basically what that means is we take certain things that look like this, we put them in this box and we call that set. And then things that look like something else, we call it by another name. And we ask, are they ever subsets of each other? If so, what can we learn from that? So we'll see that theme sort of pop up on and off throughout this semester. But the reason I keep pointing this out is I think it's important that you guys, as sort of learners, try to think of your math education and look for connections from what you remember from different classes, even ones you're taking now, and how they compare to this. So for example, Anthony's in my province stats class in 20 minutes. And a lot of the stuff we're going to do today is going to have a very clear, I don't know if it's going to be clear to you, but to the trained person, it's completely the same thing that we're doing here. Okay. Does anybody have a question about this? Comments? Concerns? Now, if you really need a reason for why we give a crap about sets, well, you're going to go find that out on Wednesday, because we're going to go to our, I mean, what's the number one thing you've been dealing with for the last couple years in your math class? Functions, right? And what does a function do? It takes something from one set and associates it with something in another set. Now, for most of what you guys have been dealing with, a function takes a number and spits out a number. That's the functions, but that's just one example of a function. A function is any rule that associates an object or an element from one set, and it associates it with a unique element in another set. So functions can be very, very, very abstract. Of course, you're saying, what do you mean? How can they be even more abstract than what we've done in our lives right now? Well, they can be. Okay, anyhow, now that we have this sort of basic idea, at least we've talked about it. Well, I've done most of the talking. There's been a few questions, which is nice. There should be more. You guys just sit there like deers in headlights and say, But then I'll give you homework, and then you guys will ask questions. Those of you, you know who you are, and I appreciate you, those who ask. Send emails and say, how do we do this? I appreciate that. You do not bother me. And then we answer your questions for you. So we'll give you a bunch of practice on this, and then hopefully you'll have questions Wednesday. And hopefully we can help answer those questions so that you learn some stuff. Hopefully. That's sort of our goal. Does anybody have a comment or a question? It's a good place to stop.
There's going to be a homework on this.
Yeah, so I'll post a homework later today. If you want to get started on it, I know for a fact, I don't have the book on me. I'm not going to try to open it right now. But I know for a fact in section 2.2 in your text, there is a table of what we would call set identities. There's probably like, I know it labels them like the commutative and the all that. If you want to start thinking about what you can do, we're going to ask you to do some of that stuff. And then we're going to also ask you to construct some specific examples, just like we did earlier. Here's a set A of some objects. Here's B. Can you tell me what A intersect B is? You know, unions and all that. Those will be the quote unquote easier problems, but you also need to understand the proofs. So anyhow, when you're confused, you ask questions, and that's awesome. So that's good. Good? All right, guys, I thank you very much, and I will see many of you later, but most of you, no, I don't know, some today, some tomorrow, some Wednesday. Take care, guys. Thank you very much. Be safe.